Good morning. Happy Wednesday. Thanks for being here. What we're going to do today is we're going to start an exam review because next Monday, when you come to class, we won't do the normal thing we've done so far, which is to turn in a problem set, seminar self-quiz, and an actual quiz. The only thing we'll do next Monday at 1:10 is we'll take this midterm. And I want to talk to you about it, let you know what you're getting into, give you some hints how to study for it and stuff like that. So for you in section L1, next Monday, which is October the 20th, again, we won't do the problem set and quiz thing. What we're going to do is take the first midterm exam, and this midterm will be over chapters 1, 2, and 3. So chapter 1 was all the intro stuff, sig figs, temperature density, blah, blah, blah. Chapter 2 was more about atomic numbers, mass number, isotopes, molar mass, moles, Avogadros. And then, of course, chapter 3 is now about the hydrogen spectrum, wavelength, frequency, energy, as well as electron configurations and nomenclature. So if you've kept up with this stuff so far, and I'm really pleased with this class, how well you've done, it shouldn't be a big deal. The format of the midterm, it'll have 12 multiple choice questions where there's 5 questions possible, and you just need to circle, tell me which one the right one is. There's also 4 short answer questions, and for those, I want to see your work. I want to see how you set things up. For the multiple choice questions, you can just put the answer down, and that's fine. But for the show your work ones, you've got to show me how you set things up. It'll go about 90 minutes in length, and the following Monday, when you turn in quiz 4 to me, I will return the midterm, and it will have what I call a summary sheet at the very last page. And the summary sheet is just how are you doing in the class as of this moment. And check that page out, all right? Once in a while I make mistakes entering grades. I want to make sure the grades you got are the ones that are actually reflected. It'll also say if you're like missing a lab or something, because if you turn in all the labs, even if they're late, you get the lab completion bonus, which is pretty cool. So just like a little encouragement kind of to check that out. Now, there is one other thing due next week, which is new to this class. I call them the Exam Prep 1 worksheet, something like that. And an exam prep is a series of questions where I'm hoping that this is all stuff that you've seen before. But I'll basically give you a question. Most of them have the answer at the end, and just show your work, how you go from the question to the answer. If you can show me how you set it up, means you've got this process down, no problem. On the other hand, you see question 4 and you're like, what the heck, Russell? I don't remember this at all. Were you smoking or whatever? Just say no, kids. But anyway, if you see something like that, reach out to me, reach out to the LSC/Avid Center people, anybody like that. I want to make sure we all have these skill sets before we start the midterm, all right? So you will turn in Exam Prep 1 at the beginning of the lab, all right, or before the exam itself. You'll also turn in the nomenclature lab that we did this last Monday. And then after the exam, we will do a lab. It's called the Identification of an Unknown Compound lab. And this is the first lab where goggles will be required. So make sure you bring them. If you don't have them, you'll have to use one of my borrowed ones, which is fine. Any questions? Any of that kind of stuff? Yeah.
Is there any chance that we could get like a small thing of notes for the exam, or?
The only thing you're going to be allowed is like on the quizzes. So a periodic table and your calculator. All right. But yeah, no notes, man. Closed book and stuff. There is a sample midterm on our website and in the companion, and I encourage you to check it out. I've tried to format it like a regular exam. There might be a few extra questions past 12 in there, but it will give you a sense like how it works, so check that out. Other questions? Okay, so what we're going to do today and for the next several days is just go through a series of questions from chapter 1 through chapter 3. And what I'll do is I'll put the question up, I'll wait for a few minutes, and I encourage you to work on the answer, all right? And you can work on paper, or you can do it electronically, whatever. If you're doing iClickers, these will be iClicker questions. You can participate, get things. And then after a few minutes, we'll talk about the answer and just see how you do, all right? If you do great, no problem. On the other hand, if there's something, this might be something to work on, stuff like that. Other questions? All right. So here's a question that is from the density area, all right? And in this problem, we have some piece of metal with a mass of 33.2 grams. We drop it in some water, and initially there was 10.0 centimeters cubed. Use this data and this picture to figure out not only the density of your metal, but then also the identification of the metal. So see if you can figure this out on your own first. We'll talk about it after a few minutes. Okay, so density is a cool relationship between the mass of an object, which is like how many grams it has, and the volume of the object. It can be in centimeters cubed or milliliters. Either way is great. And if you can find it, there's lots of things you can do. In this one, we're actually using the density to identify the identity of the metal, which is cool too. But the punchline here is that metal density is mass over volume. So we have the mass of the metal, no problem. That'll be in the numerator. And then in the denominator, the bottom, we want the change in the volume. It's like the final volume minus the initial volume. And up here are the actual values for the volume. So in the bottom, you put 22.3 minus 10.0, which would be 12.3 centimeters cubed. So it's like 33.2 grams divided by 12.3. Density comes out to be 2.70, and on this list, that's certainly closest to aluminum. So one use of these densities is to find the identity, although more often than not, scientists are more just anxious to know what the density is so you can relate it. Cool. Any questions? Sweet. Okay. Here's a question we did look at earlier, but I think it's worth talking about again. These are 3 temperatures that can be found on the Earth. The difference is, though, however, one is in Celsius, one is in Fahrenheit, and one is in Kelvin. And I'd like you to put them in order of increasing temperature, so from smallest to largest. Now, if there's ever a Fahrenheit question, I will absolutely give you this expression right here because it's just lame. But on the other hand, I would like you to know Celsius and Kelvin. So see if you can figure out this range of temperatures from the lowest to the highest. We'll talk about it here. What number do we use to go from Celsius to Kelvin and Kelvin to Celsius? My man, 273.15, right on. Now in this problem, since the Kelvin stops at the 1 spot, you can just use 273, but like Ryan used, I prefer you to know that number definitely. But why that's important is that to go from a Kelvin to a Celsius, you subtract 273.15. So 256 minus 273, it's going to give you a negative number, all right, a negative Celsius number. So what that means is that this will be smaller, excuse me, than the 29 Celsius value. So we at least know that this one goes before here. Now for the Fahrenheit, you just about kind of have to do this unless you're used to Fahrenheit to Celsius, which is something I've done since I've used Fahrenheit way too much in my personal world. But if you haven't, here's what I would do. 45 is this, which equals 1.8x plus 32. So if you first subtract 32, 45 minus 32, it's about 13, then you divide by 1.8 to get the Celsius temperature. You can also use 9/5, either way is great. When you do that, you don't have a very big number. It's positive, but it's not super big. So what ends up happening then is the 256 Kelvin is actually the smallest number. It's the biggest magnitude, but it is actually the smallest number when you convert to a common system. So with Celsius, here's the 256 minus 273, cut it off at the 1 spot, minus 17 degrees Celsius. That certainly is smaller than 29 Celsius. And then here is the Fahrenheit 45, We subtracted 32 divided by 1.8. It's about 7 degrees Celsius. So it's in between the Kelvin and the Celsius value. This would be the order. Smallest would be 256, largest would be 29. Celsius is usually what it is, but Gabe decides to turn everything to Kelvin. That's fine. All right. I would just keep it in Celsius, but whatever you want to do. Any questions on that? All right. Here's a similar problem, but this one has length, all right? These metric prefixes are going to pop up a lot, so the numbers are all over the place. In a problem like this, what I would probably do is I would probably turn everything into meters, all right? But what you want to do is put them in order of increasing size. So the smallest first to the biggest last. See what you can do with this. All right, the metric system, super cool because you can express really big and really small quantities using these prefixes. And even though there's a whole bunch of them, these 5 up here, I want you to know, all right? So get ready. The 5 are kilo, centa, milli, micro, and nano. And they each have a corresponding number with them. So for example, we've done a lot in the last week or so with nanometers. Well, how you use these is 1 nanometer equals 10 to the minus 9 meters. And that obviously is useful when it comes to visible light. A lot of times what people will do is they divide both sides by 10 to the minus 9. 10 to the minus 9 on the bottom becomes 10 to the positive 9. So you can also express this as 10 nanometers in 1 meter. And either way is okay. All right, you pick the way that you want to. Now for this problem, The base unit is the meter. And you can see up here, two of them are already in meters. So 2.3 meters is certainly bigger than 0.125. But we also have a centa and a milli. So a centimeter would be 10 to the minus 2 meters, and a millimeter is 10 to the minus 3 meters. So again, what I would do is I would convert everything over to a common unit. So 9 centimeters is one of the things we want to convert over. And this says that 1 centimeter is 10 to the minus 2 meters. So again, the beginning unit cancels out and you've got meters left over. This comes out to be 0.09 meters. All right, so 0.09 is smaller than 2.3 and 0.125, but that's kind of how you would do this kind of process. And you do something similar for the millimeters to 15 millimeters. Now you can use, like this one right here, 1 millimeter, 10 to the minus 3 meters. All right, again, that cancels out. 0.215 meters would be the value. So if you look at all these numbers then, 0.09 meters is actually the smallest of all of them. And because we want them in increasing size, 0.09 meters or 9 centimeters would be first. And then 215 millimeters, 0.215 meters, that's bigger than 0.125. And of course, 2.3 meters is bigger than all of them. So answer D here would be the right way to do it. Again, try to translate the ones into a common base, so then that way you can compare them just easily and stuff. So, and again, somebody wants to use 1,000 millimeters per meter instead of 10 to the minus 3 meters per millimeter. That's totally fine. Questions? All right. All right, well, enough of this metric crap. Now let's get into the gist of atoms, all right? We have here a neutral atom of iron 58. And I'd like you to tell me if one of these here represents the composition of the atom itself. And the composition in this problem would be protons, neutrons, and electrons. So see if you can find out if one of those is right. Maybe not enough is given. Hint, it's not D. See what you can do. a problem like this, you need to know what the symbol is for iron. Does anybody know what the symbol is for iron? Fe, that's right. Now, if you don't know that Fe is iron, your periodic table will be able to tell you totally. All right, the one we're using, the names are listed as well as the symbol. But of course, if you know what it is, it can be cool. Why you need that symbol today is because this number, the atomic number, represents the number of protons. So in this problem, the number of protons must be 26, all right? The atomic number, the whole number listed on the periodic table, is always equal to the protons. And since this is a neutral atom, how many electrons will it have? 26, that's right, same number. So this thing is going to have 26 protons and 26 electrons. So it's either going to be answer D or it's going to be answer B, all right? So the last piece of information that we need is the number of neutrons. And the dash number that sometimes happens for these, that's the mass number. And mass number, protons plus neutrons. So if you take 58 and subtract the number of protons, it's like protons plus neutrons minus protons, you should end up with 32, all right? So this thing has 32 neutrons, 26 protons, which comes from the atomic number, and because it's neutral, it'll also have 26 electrons. Okay? Any questions on that? Cool. The other number on the periodic table, the molar mass, atomic mass, whatever you want to call it, is going to be more useful to us, definitely. And we need to talk a little bit more about how those numbers pop up, because they're all based on statistics. So imagine you have some element E, and the mass numbers there are 72, 73, 74, and these are the relative percentages. So think about then what the best value for the atomic weight, atomic mass of this element would be. All right, so see about what there's a math way to do this problem, and there's also kind of a hand-waving way to do this problem if you think it through. And either way you do it is fantastic. if you don't want to do math, and I won't take names of anybody that doesn't want to do math, but if you don't feel like doing math right now, the non-math way to do this is to realize that those mass numbers, which are 72, 73, and 74 up there, they fall like on a number line. And why that's important is that you can think about then what the probable average of those values are. Now, if you had like close to 100% 72, then the number here, the average value, which is what the atomic mass / atomic weight is, the average value would be really, really close to 72, all right? If you had almost 100% 74, then the average would be definitely closer to 74. You have, though, a lot more of the 72 isotope than you have 73 and 74. So that's going to push it left, I would think, of 73. So my best guess here would be that it's probably going to be the 72.8 because it's closer to 72 than it is to like 74. It's pulling it, but it isn't that much more than 50%, all right? It's not going to be this much. Like this would probably be like 90% 72 or something like that. These two are big enough that I think it's going to pull the average to the right. So this would be my hand-waving guess, all right? And you can see what it is. But there's another way to do it too. You can also take the decimal version of the percentage, so like 0.545, and multiply it by the mass number, so times 72. And you do that for each of them, add them together to get the value that way. So if you want to do it the math way, that's cool too. 0.545 times 72 plus 0.156 times 73 plus 0.299 times 74. And that would be another way, the math way, to get what the actual value is. But either way, it does come out to be about 72.8. So here is the math version, all right? I took the 54.5% and divided by 100, so 0.545, and multiplied it by 72. And then I added it to the 73 and the 74. Make sure you use the decimal version. Pretty good, stuff like that. But honestly, either way is cool, and it doesn't really matter which way. This is the process used to get all of the atomic mass / molar mass values on the periodic table. They're all averages, all right? Depends on the isotopes, depends on the masses, depends on the percentages, but hopefully by figuring out how this works, then you can see where these numbers come from. They're not just given to you, science. Questions? So here's another question with how all of these things work out. In this particular question, we're forming the strontium 2+ ion. And one of those statements up there is correct. See if you can use your understanding of protons, neutrons, electrons, etc. to figure out which of those would be the best answer. All right. So strontium is number 38 on the periodic table right there. It's named after some city in Scotland or something like that. 38 means that neutral strontium would have 38 protons. And if it's a neutral atom of strontium, how many electrons would it have? 38, that's right. Same number. If it's neutral, protons and electrons are the same, all right? So the question is then, what happens when it becomes strontium 2 plus? Now, are you going to change the number of protons, making it a positive 2? No, I see lots of you shaking your heads. Absolutely not. That's right. If you change the protons, you change the actual atom itself. So if you take away a proton, for example, strontium would become rubidium. And if you gained a proton, strontium would become number 39, which is yttrium. So you're not going to change the number of protons. Now, protons are positive and electrons are negative. So what's happening when you make a positive 2 ion?
Losing 2 electrons.
Losing 2 electrons. Well done. You can actually write them, if you want, as like 2 electrons getting kicked out, like that. So instead of having 38 electrons, now it's going to have 36 electrons. 38 protons, which each are plus 1, and 36 electrons, which each are minus 1. That's where the positive charge comes from, all right? So by losing 2 electrons, that's what makes it a positive 2 ion. So this thing is going to lose 2 electrons. It's not going to lose 1 or 3 or something like that. And as you can probably see, strontium, if you go backwards, minus 1 electron would be rubidium, but minus 2 electrons then would be krypton. So this crazy thing, answer C, works really well. It loses 2 electrons, it doesn't gain. It loses 2 electrons, and now it has the same number of electrons as krypton. So in the noble gas configuration stuff, this is kind of cool to know. Strontium 2 plus wants to be like one of the cool kids in the back of the bus. Yeah. Any questions? Okay. In this picture, we are looking at emission lines. And emission lines are exothermic, they give off energy. So this is the Bohr model of the atom. And in the Bohr model of the atom, electrons start at a lower n and go up to a higher n. That's absorbance. We're actually looking at the opposite. We're going to look at when you go from a higher n down to a lower n. And what I'd like you to do in this problem, tell me how many emission lines are possible using this particular diagram, all right? Using the first 5 levels for hydrogen, how many emission lines do you see? We'll talk about this here in a little bit. So on this problem, we're talking about going initially from a lower end to a higher end, and this takes energy. It's endothermic. So if you go from a lower end to a higher end, this is what they call absorbance. And in a lot of spectroscopy, if you watch CSI show stuff like that, that's what they measure, and it's a really cool field. But these aren't emission lines. After the electron absorbs energy and goes to a higher end, after a while, they feel like they get homesick, all right? And they want to go from a higher end to a lower end. And those are what they call emission lines. And that's what we studied last week. That's what you saw in the spectroscope. Those sharp line spectra were the result of these emission lines. So in the Bohr model, all right, first of all, notice that they actually go all the way up to infinity. Down here would be the nucleus. So the electrons down here would be, this would be the ground state. It takes up energy to get away from it, but as they come back down, they actually release little energy in the process. So in a problem like this, first of all, note that it's 1 over n squared. So the n values get closer and closer and closer as you get up. So the difference between 5 and 4 is actually smaller than the difference between 5 and 3, stuff like that. This is an energy axis, right? It's all about the energy when it comes to chemistry. So when it comes to these things, then these numbers will be different, and we'll talk about that a little bit here. So in this problem, considering these 5 lines, if you want to know the emission lines, I would start at n equals 5. And you can have 5 to 4, that would be one transition. You could have 5 to 3, 5 to 2, 5 to 1. So that would be 4 transitions right there. But you don't have to start at 5, you can start at 4, all right? You could have 4 to 3, 4 to 2, 4 to 1. You could also start at 3, go 3 to 2, 3 to 1. And finally, you could start at number 2, and that 2 just goes 2 to 1. But you always want to go higher end to lower end. So if you count all of those up, you end up with 10 lines possible. Those 10 lines are the result of hydrogen making different transitions. Now, bonus question, where did the lines stop? What was the final end value for the visible lines in the hydrogen spectrum that we calculated last week? Yeah, my man. They all ended up at n equals 2, all right? So all the visible lines that we saw, the red, the blue, and maybe 2 purples, they were like 3 to 2, 4 to 2, 5 to 2, and even though it's not showing here, it would be like 6 to 2, yeah. The ones that ended up at n equals 1, those were ultraviolet. The ones that ended up at n equals 3 were infrared, and we can't see those, and our spectroscope didn't work very well for those anyway, so it's not very cool. But now you can hopefully see what's going on. And again, no one had any idea where the sharp line spectrum were coming from until Bohr came out with his model. In the lab, we used minus 1312.04 over n squared. That's what we calculated, like 1, 2, 3, 4, etc. This number came from the Rydberg constant, Planck's constant, speed of light, as well as Avogadro's, and I think there was a joules to kilojoules in there too. You don't need to worry about that, but hopefully you're starting to see like how this worked out. And no one had done anything with sharp line spectra until Bohr started to think about this, which was kind of cool. Questions? So, knowing that this is an energy axis, we can take it one more step further, all right? So a 1 to 5 transition would be a pretty high energy compared to, say, a 4 to 5. The gap is bigger than 4 to 5. So which one of those transitions that we just mentioned would have the highest frequency? All right, so use your knowledge about how energy and frequency go together and see if you can figure out which of those transitions would have the highest frequency. Talk about it here in a second. I see a lot of thinking on this question, which is really cool. So these diagrams, this is an energy axis. So the biggest energy would be the biggest arrow going from top to bottom, and the smallest energy would be the smallest arrow. And that's important because energy equals h nu, where nu is the frequency. So if you want the highest frequency, you want the highest energy. You want the biggest energy gap. And of those, the 5 to 1 is the biggest arrow. Like going from here to here would be the biggest arrow, all right? That's the biggest delta E, and biggest delta E would be proportional to the biggest frequency. So it's all coming together. It would also be the smallest wavelength if you wanted to go there. So, questions? All right, we'll do more of this on Friday. Have a wonderful day.